Now, I will talk about inductance again in this short video, but this will be about a different kind of inductance. So I have a loop, and let's say that there is current flowing in this loop. I only have one loop. This current I will create a magnetic field in the area around this loop. Now, this magnetic field will be present in the loop itself, which means I will have a magnetic flux going through this loop due to the fact that there is current in this loop. Okay, this is slightly different. We have done so far, we have seen how to use Faraday's law and talked about magnetic flux going through a loop, but that was due to a current flowing in a different loop. Now I'm talking about in a single loop. The current is flowing, it's creating a magnetic field around it, and that magnetic field, the presence of that magnetic field, results in a flux going through this. Now, because I have a magnetic flux going through the loop, I can say that this magnetic flux will be proportional to the current that flows through the loop. And I want to tell you what the justification for this is. We know from Biot-Savart's law, say a small delta B mu naught 4 pi I delta L cross r hat divided by r. Okay, the magnetic field will be, from Biot-Savart's law, the magnetic field will be proportional to I. And if the magnetic field is proportional to I know the definition of the magnetic flux is the surface integral of B dot dA. Okay, if B is proportional to the current I, then the magnetic flux will also be proportional to the current I. Now, we call this constant of proportionality between the current in this loop and the flux that goes through the same loop, this is what we call the self-inductance. And it is a little bit weird to think about the flux that the loop itself creates, but it is important to take it into account in some physical phenomena. Now, because we have this relationship between the flux and the current that flows through the loop, I can use Faraday's law to find the induced EMF and this will be minus d over dt L times I, because L is a constant, does not depend on time, minus L di over dt. Now, what does this mean? Okay, this is the induced EMF. I want to remind you, I have a single loop. This is the current that flows through the loop, and this is the induced EMF in the same loop. Which means anytime you change the current, anytime you have a change in the current, due to that change in the current, you will induce an EMF, importantly, on the same loop. Okay. This is the first time I mentioned this. A change in the current in a circuit, in the loop, will result in an induced EMF on the same circuit, on the same loop. And if you know this constant, the self-inductance, you can calculate that induced EMF.